All right, so everybody, hello. And so my today's lecture is a continuation of previous lectures. So today I will talk on superconducting qubits, as well I will talk on semiconductor qubits. I will maybe start to share some screens. So 1 second. Yeah. So basically, this is quite important to say that we will talk about semiconductors, and we will talk about superconductors. So there is a qualitative difference between semiconductors and superconductors. Please let me know if camera is visible, right? I mean, please give me some comment on the chat. So do you see the screen with white sheet of paper? Please give me the comments so I can start. So so basically we have the key difference between semiconductor and superconductor is the ability to screen the magnetic and electric field. So what happens is that in superconductors is almost a perfect material that shields magnetic field, external magnetic field of certain amplitude. And and also if we consider electric charge behavior in semiconductor, electric charge will behave in such a way that it will try to diminish, try to reduce the global electric field that is in semiconductor. So there is a tendency for magnetic for reduction of electric and magnetic field both in superconductor and in semiconductor. So if we have a how to say, if we want to consider the behavior of single electrons in semiconductor, we will look for its equations of motion, but this equations of motion will lead to the these equations of motion will lead to such configuration of electric charge that electric charge is globally minimized in semiconductor and in external space. So that's a quite important feature to underline. Yeah, so let us deal with semiconductor and superconductor at the same time. And so maybe I will start a brief introduction to this. Maybe I will start a brief introduction to qubits, to semiconductor qubits. So basically, we have two types of semiconductor qubits. Eigenenergy-based semiconductor qubit and position-based semiconductor qubit. So I would say that that basically most implementations of a quantum technology is based on the usage of eigenenergy-based qubits. However, in 2004, there was attempt by Fujisawa and Peta, Fujisawa from NTT and Peta from Princeton University, to implement single electron devices in semiconductor. So, the key feature was that one can has how to say, if we use a chain of couple semiconductor qubits. So let us consider the system with two semiconductor qubits and with two semiconductor quantum dots that are interconnected. So if we place the single electron in the system of coupled quantum dots, this single electron wave packet will be distributed among all connected quantum dots. If we have the situation where there are only two quantum dots, then the presence of electron on left side will correspond to logical 0, and let's say, and its presence on the right side will correspond to logical 1. And in such case, it turns out that it is beneficial to use so-called Wannier representation of wave function, which is about the usage of maximum localized wave function. And in such case, basically, okay. So I hope is a white sheet of paper visible to you with a pen? Please let me know by chat, because I'm not so sure. So yeah. So okay. So Radek, could you please let me know if screen sharing is visible? Can you see the pen?
Yes, yeah, I can see.
All right. Okay, so let's say, so we are talking about semiconductor qubits. And basically, I specified two categories: eigenenergy-based qubits, and it's using orthogonality of eigenenergy wave functions, more exactly orthonormality of eigenenergy wave functions. I would say 95% of a quantum technology is associated with this. And with this solution, and second idea is use of Wannier function, or in another way, position-based qubit. And this is using orthogonality of maximum localized wave functions. And this is so-called Wannier functions. This is Wannier functions. So basically, Wannier functions. Yeah, I will mention about this thing in detail. So, so what is the difference? So basically, I will give you example. So basically, if you place, let us consider the effective potential of such shape. Let's say this is Vx x. Then there are various solutions. So this corresponds to E1, and this corresponds to E2. So basically, we have a situation where we have certain energy levels, and we are exploiting this difference between energy levels. So essentially, the quantum state can be written as, let's say, gamma E1 plus gamma E2. So it's a superposition, right? So obviously, there is normalization condition. So there is bound state. So in order to operate with such type of qubit, you need to be able to control the population of each energy level, and then you can use microwaves in order to excite the system or de-excite the system. You have to use basically time-dependent electric field, or you can use time-dependent magnetic field. And such qubit is not exactly the most suitable from nanotechnology point of view. This is because you have to use microwaves basically, and this is like spacey, like space, and there is no much what you can do about the reduction of this psi, about the scaling down this system. So this is eigenenergy qubits. So basically, yeah, I imagine that there are certain materials you can place. So also you can place, yeah, semiconductor one, semiconductor two, semiconductor one again. So you have such sandwich of materials, and then you have to look for its, so there is a kind of single quantum dot loop that you can implement. Also, you can do quite much the same things if you replace semiconductors with superconductors, and you can place insulator in between, then you can have it. Okay, so this is eigenenergy qubit. So this is a kind of traditional qubit, let's just say. But so this was example one, and there is example two. In example two, we are changing the strategy of approach. So you have to be aware that this is a little bit beyond our imagination, but CMOS technology is still developing, despite many years of previous development. So for example, there is a company in Krakow, whose name is Silicon Creativity, and it has headquarters in the US, but most workers are localized in Krakow. And they recruit people from AGH University, and that they have the ability to design circuits in cadence. And the company is localized quite close to Institute of Nuclear Science, Polish Academy of Science, Nieuwdowszański Institute. And they already operate with they use transistors that has only 3 nanometers of channel length, and people are still trying to reduce its size. So more or less, it's 30 angstroms. So it's less than 30 atoms in one line. So definitely we are approaching the size of atom as we're in our information processing. And mostly we are using the structures for classical information processing for analog circuits. But at the same time, we are entering quantum regime, especially if we cool down the system. It is also a very remarkable feature of CMOS technology that if you have a very small channel length in CMOS transistor, what happens is that instead of thermal activation of electric charge, as we have in classical semiconductor electronics, you're having the activation by gradient of electric field is generated by the gates. So if you apply half volt, if there is a potential difference of half volt between gates, and if it acts at the distance of 30 angstroms, there is a very big gradient of electric field that is able to accelerate the electrons, or the accelerated electrons, or holes, and this so some of them can become carriers when they're bounded to atoms. So there is mechanism of electric field activation of electric charge. That's a new qualitative feature in CMOS electronics, in semiconductor electronics. It's not so common knowledge right now, but people start to deal with such approach. And there is already an attempt worldwide that is overtaken and to implement so-called high-temperature semiconductor qubits. What I mean by high temperature, it's, let's say its operation is at 4 Kelvin, liquid helium temperature of liquid helium-4, which is considerably less expensive than the case of traditional semiconductor, traditional qubits that are, for example, used by IBM. IBM is using transmon resistor junction qubit, and basically they need to be cooled down to 30 millikelvin. So people are trying to go to much higher temperatures. And also what needs to be said is that the quality of semiconductor films is very high, because if it would be not so high, what would happen is that simply there will be electric breakdown, and this is not taking place. So that's a kind of confirmation that number of defects in semiconductor materials is really low. So because of that, people are trying to think that why we shall use resistor junctions that are, since they are big, they take 3000 angstroms, not 30 angstroms. And it also needs to be cooled down to 30 millikelvin over time. So why not to use electrons, single electrons, and semiconductor material? It is already very well integrated and there are billions of transistors on one chip. So perhaps everything shall be controlled by electric field, not so much by magnetic field anymore. And you know that the key difference between semiconductor qubits is that semiconductor qubits are essentially controlled by electric field, while superconducting qubits are essentially controlled by magnetic field. So, so there's certain duality between two qubits, and there could be, one can find certain analogies. Let's say it's okay. So let me maybe move to the example of position-based qubits. So essentially, we need two quantum dots. So quantum dot 1, quantum dot 2. There is some interconnection. So there is semiconductor 1, semiconductor 1, semiconductor 2. And there is some barrier, and usually what you are doing is you are placing 3 electrodes. So you bias 1 electrode to VG1, another electrode to VG2, and third electrode to VG3. So what does happen is that if you write down the effective, so we are talking right now about confinement of 1 electron. It can be more than 1, but this is more complicated situation. I'm not going to mention about in such great detail about this more complicated situation. So what basically happens is that you might have such situation that your effective potential is of such shape, and then your wave function is, let's say, more localized on one side. So you're essentially having to you have essentially 2 maximum localized linear functions left and right. And what is the key feature is that having such a presentation, you can write this maybe alpha VL plus beta VR. So here we have this orthonormality principle, which basically says as this, that states are orthonormal. Here we also have this Pj. This is also like that. And the difference is that that left maximum localized left linear function and right linear function is a linear superposition of 2 eigenenergies. So that's you can always transfer your picture from eigenenergies description into linear function description by using unitarian transformation. So then you are dealing. So in a sense, probability, let's say, probability for a logical state value 0 is nothing else as alpha beta, and probability for logical 1 is beta square. there's a theorem that says that in order to so you always have oscillations of occupancy. So this so here there are oscillations of occupancy on the left side and right side, and these oscillations of occupancy are proportional to energy difference between eigenenergies. So if you only have one eigenenergy populated in a chain of two coupled quantum dots, there is no possibility of implementation of semiconductor positionless qubit, electrostatic basic qubit. But if you at least populate at least two eigenenergies, then there is a possibility of implementation of logical state of 0 and 1 at the same time. So there is a superposition principle. So how this guy is translated to semiconductor physics further. Essentially, what happens is that you might have a semiconductor nanowire, and you're placing some free insulators. There's insulator, insulator, insulator. There is the semiconductor nanowire, and this kind of distance can be, let's say, from 20 to 3 nanometers, depends on the technology. And then you put metallic gates on the top, and then this is just have it. Yeah, this is VG1. Yeah, maybe 1, and this is 3. Okay, so VG1 is controlled by voltage VG2, and this is controlled by voltage VG3. So basically, you are using planar field effect transistor, and you can generate any type of potential. Well, maybe not any, but quite big family of potentials that will control. So this is one of the possibilities. And obviously, you are generating such potential by having free controlling voltages VG1, VG2, VG3. VG1, VG2, VG3 are controlling voltages. The common belief is that, so in Europe, Sekle Institute does specialized in CMOS technology, but mostly oriented on a kind of eigenenergy qubits, but still they were doing both actually. And the key disadvantage of semiconductor qubits is the coherence time. So the coherence time basically is in the range of nanoseconds, while in superconductors it can be 500 microseconds, and then people are approaching 2 milliseconds right now. So there are 3 orders of magnitude higher the coherence time, but at the same time, scalability of CMOS technologies is no comparison with scalability of superconducting qubits. So there are advantages and disadvantages of each implementation, and this leads me to another motivation to assume that we are able to construct both types of quantum computers. And having so, we will come to a situation where we want to simply integrate those technologies together. And this is one of the topics for today's considerations. Okay, but before doing it, I will spend some time on analysis of properties of semiconductor qubits. All right, so what's the central so how things will look like? So obviously the system is biased by electric field, and just to let you know, you can have nanowires that are biasing the free electrodes that you see here. So you can have nano cables as well. And as you know, microwaves requires waveguides. They're basically of gigahertz frequencies, and it takes space, and you cannot have so many waveguides in the system. There are problems with its integration and so on and so on. All right. Okay, so so what will be the system description? So the system Hamiltonian, well, so this will be tight, maybe tight binding description of semiconductor position-based qubits. Position-based qubits. So it will be convenient to have localized energy on the left side. So just to let you know, if you put very high barrier in between, so here is state is quite much delocalized, and here quantum state is localized. So it can be here, it can be here, and you can isolate these quantum dots if you put very high barrier in between. So there's no possibility of tunneling by this barrier. Yeah, so localized energy on left, right. So okay, so we can have XL. So I can write it in such a way. So let me start first from the case of isolated system. It's like this. Left position of quantum dots. So it's basically this corresponds to QL and Q right. Yeah. So and there's a possibility of tunneling. Tunneling from left to right, and so it will be like that. And tunneling from right to left, like this. And what is also remarkable is that we at very beginning we consider a system without dissipation. So basically those guys are real values. However, if there is dissipation, and okay, so let's know dissipation at first. I mean, dissipation in quantum systems is another subject, no dissipation. So entity L right, the hermicity condition for Hamiltonian. So those guys can be complex value. It will be convenient to write R, maybe, okay, maybe small r. imaginary part. So obviously, this is nothing else as TR, and this is minus. And in such case, TR, TL are real values. Yeah. So there is no dissipation. However, if there is dissipation, then, for example, then this can be written in such a way, and yeah, and then obviously LA, LB have a real value, so real values, and as well with dissipation. Dissipation can be like, for example, escape of a fish bucket outside. Can be also counted as. So basically, there's very nice analogy that we have two quantum dots, and these two quantum dots. So this picture, two quantum dots. So we have left and right. It's a kind of equivalent if you have a wave resonant cavities, classical resonant cavities. So you have left cavity, right cavity. There is a weak interconnection, so there's eigenmodes of resonating electromagnetic field in the left and right. You can also electrically or mechanically turn, put the barrier, so the eigenmodes are independent, and they also can be codependent. So there is electromagnetic cavity analogy. And this energy, can be scaled more and more, because you can add this here quantum dot, also you can here add another cavity, and so on and so on. So you can move on with this analogy. All right, but let us first concentrate on this Hamiltonian. So maybe I will put it in such a way. So basically, we are dealing with such matrix structure, and then I cannot make mistake. RL T L R. Okay, I will write it on next page. It's such Hamiltonian operator. So basically, maybe it will be beneficial to think. So we are dealing with such type of Hamiltonian, right? And there is tunneling TS, complex value. Let's say. This is Hamiltonian of position-based qubits are electrostatic qubits. This is maybe most minimalistic of position-based qubits. Obviously, we can use Schrödinger equations as well, but this Hamiltonian has its own beauty, and let me go even further with its beauty to show you how simple and deep this approach can be. So essentially, I want to underline that I have created quite lengthy. Yeah, so there is kind of yeah, that's the title of this my approach. So analytical solutions of an electron interacting system confine a graph of coupled quasi-static semiconductor and superconductor quantum dots entitled by the model with focus on quantum machine processing. You can get such it's almost 100 pages text, but I am making this approach even longer, and everything is analytical, so it's quite beautiful. So I'm doing everything type binding, but also there's possibility of doing this in with usage of Schrödinger equation. And in case of coupled in a coupled semiconductor qubits, one deals with algebraic equations if one uses type binding model, and one is dealing with Schrödinger equation with integral differential equations if one is inspecting the properties of coupled quantum dots. And there is work of Professor Shafran on this, Bartłomiej Shafran. There's also my work in type binding model, also did such things in with usage of integral differential equations. I have one paper in SPI proceedings. If you Google SPI Pomorski proceedings, then you will find my approach to this problem. You can Google Bartłomiej Shafran, and then you will find his physical review quite recently published. Yeah, so there's a bunch of papers. So I already issued like 8 archives that are specifying the usage of type binding model. Since there is a heavy competition in quantum technologies and heavy competition in theory of quantum technological systems, I decided to go for a kind of hybrid qubits. Yeah, I also can recommend two single electron lines paper also published by me and my coworkers. And then everything was analytical in this paper. In this paper, I have a chain of 3 connected quantum dots, and basically they were interacting. So free. So what I did in this paper, I will later describe it. So I have such a system. Professor Shafran approach was use 5 quantum dots with semiconductor. Yeah, but so was 2 single electron lines in type binding and 2 single electron lines in Schrödinger approach. Yeah, so there is Professor Bartłomiej Shafran 2020 and my work 2019. Yeah, so we are complementary at some point. I will try to arrive to this. You can Google by yourself, but also we'll try to give you some connections. Okay, let me first inspect the properties. So, case of maximum delocalized electron in system of 2 coupled quantum dots. So we have the same quantum symmetric system. So Q dots 1, Q dots 2. So what is, I will at first make it real. TS becomes complex if we send some electric currents by outside we can generate some phase imprint on this left and right quantum dot. And this phase imprint is due to Aharonov-Bohm effect. And so then this TS becomes complex value. But let us first consider makes TS to be complex value. Right. This source of external magnetic field. Let's say more exactly, this is the source of external vector potential. All right, and so what is, let's say, if we have a symmetric system, we can set AP. So essentially we have such system as here. This is our effective potential. The same bottoms. It's very essential, so we have the same dimensions. Li is equal to Lb not to L. It's very essential. The same potential, symmetry of this potential, right? Left and right. And in such case, the Hamiltonian becomes simply AP. Let's say TS is really variable, but okay, maybe even a complex. There's such potential as the Hamiltonian as here. So this is just recognize it's not potential energy of it's not energy of potential, but it's energy localized on the left side and on the right side. So what are the eigenenergies? It's very simple. AP minus E square minus TS square set to 0, such equation. And then it simply turns out that your eigenenergies are AP plus minus TS. To eigenenergies. It's quite essential. Yeah. So, okay, to have a single electron, you can confine it by certain potential, but it will try to be delocalized. So sooner or later, it will try to escape from your confined potential. So in order to tackle such problem, you need certain, so you mentioned from a technological point of view, you have isolator, you can put as many gates as you like, metal 1, metal 2, metal 3 and 4. So you can try to, so somehow this wave function is something like this. So you have, if it tries to escape, you need to push, activate certain external potentials and try to keep it bounded as much as possible. It's not so easy. There are certain approaches how to do it. So there were first experiments done by Fujisawa from NDT in Japan. He was working at Delft University for a while, and later there were attempts to by successful attempts by Peta from Princeton University and Jason Peta. There's like 10 Nature publications. Yes, so he was implementing more complicated structures. All right, that's how it is. So basically, so basically you are dealing with such description of your quantum state. Of course, you can have more. If you have more quantum dots, you have more contributions. All right, and yeah. So now let us move to the case of interacting qubits, and then I will briefly describe this concept of yeah. So what is so if I have an electron, there will be anti-correlation principle that will work here. You have two coupled double quantum dot systems. So basically Q dot 1A, Q dot 2A, then I have Q dot 1B and Q dot 1 and 2B. If I have electron here, I have a tendency to have electron here. I mean, this is anti-correlation principle. Electrostatic repulsion takes place. And this, there's anti-correlation of presence of positions of electric charge. Simply because if there is a higher electrostatic energy, if two electrons are here or here, right? So obviously, the ground state energy is minimized. Classical ground state energy is minimized like here, but obviously we have, in a quantum case, we can have a superposition of both energies. You can search by yourself. There's also written in the manuscripts, I mean. So this is classical ground energy configuration, and there is a quantum, there is a superposition, quantum ground energy representation. All right, we will inspect this in greater detail. Yeah, but before moving to this, let's still refer to this example. And yeah, so basically what happens is that your ground energy is VL, ground energy is VL minus VR. This is your ground, and excited is VL plus VR, like this. So there's a combination of symmetric and asymmetrical. So there's a combination of symmetry. So this is ground energy, quantum state for qubit. And this is first excited state for qubit. This one. So it's very nice to write that this is, there is naturally Hadamard transformation present. Yeah, so you can write this as matrices. All right. Yeah, so now we are dealing with two electrostatically interacting qubits, symmetric single electron lines. All right, so how to deal with that? First, we need to write down the Hamiltonian. So again, we have Hamiltonian of I look for right to left first, the upper, LA. Right. Yeah. And then we have this. Okay, I will just use the SA to do some variant that way. Yeah. Times identity for second system, P plus identity. Okay, again the same. So this is a little bit monotonous. And then I need to write down the Coulomb electrostatic direction. I will just do it, and I will show you the explicit structure of this matrix. Plus, and then, yeah, all right. So we have 4 possibilities. So we have well, 2 distances. Distance 1 and distance 2. Distance 1, right? Distance 2. Distance 1, we have such situation as L, LB, LL, LB. Again, symmetric. That is your right and right, and then L, right B. Plus D1 again and D2. Then we can this is RP. Yeah. So that's kind of lengthy expression, but the identity A is nothing else as projection on state on itself. So it is given as this. So LB Right. So we have this project representation of the Hamiltonian, and then we are ending with matrix structure. Speed up. Sorry for lengthy. So we have a situation. So basically, our quantum state is LP gamma 1 plus XL. Okay, it's like this. Like this. So this is right here. Gamma 2 plus okay, LB gamma 3 plus it's RA RB gamma 4. There's only 4 possibilities, and the sum over all this sum of probability over all 4 possibilities is set to 1 in the system that is non-dissipative. All right, so how are we going to write down the Hamiltonian? Okay, I will do some certain things from my memory, since I'm dealing with this guy for a long time. And I will explain the structure of Hamiltonian, how it just did happen in a certain way. All right, point B. And I will probably conclude on this Hamiltonian structure today. B, and this is RE plus RB. The diagonal terms plus Q square over D1. This is in symmetric case over D1. And there is a Q square over D2. Q square over D2. These are diagonal terms given. And there's a halting term for seconds. So such structure is given as here. And again, there's halting term for TS, TSB. All terms on anti-diagonal turns out to be 0. In time-independent case of Hamiltonian. And yeah, because we look for a Hamiltonian that is Hermitian. And the rest terms is a halting constant. Is a halting constant TSA, 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 TSA. This is from Hamiltonian 4 by 4. And this is 4 eigenenergies. And such Hamiltonian can always solve, since it leads to polynomial of 4th order. Okay, we are going to deal with solutions in some time.